It's with great pleasure that I welcome on stage Nathan Guthrie of Hewlett-Packard. Nathan has come over from the USA. He's a senior member of a team using Witness at the HP location in Oregon. Nathan's going to describe a couple of projects that he's been working on and explain how he uses Witness at HP. Thank you, Nathan.
This,
all yours.
Just goes up and down.
There you go. Thank you.
All right. Good morning. I'm Nathan Guthrie, and like Jeff was saying, I work at HP. In case you haven't heard of HP, we're the world's largest technology company, and we do printing, so printers, personal computing, also server software and services and IT infrastructure. And just a couple of interesting statistics, I guess. We've got about 350,000 employees worldwide. And as far as printers go, we ship about 1 million printers every week and 48 million PCs annually. Now getting down to the Corvallis site, in case you don't know where Oregon is, it's just south of Washington. Corvallis itself is about 200 miles, or I guess that's 320 kilometers south of Seattle. Just kind of orient yourself way over on the west coast. The Corvallis site itself is a new product development and a proto manufacturing site, and we're situated within the printing personal systems group. So mostly focus on the printing industry. And at our site, Witness is used both in the support of manufacturing operations and in new business evaluation and analysis. So on the new business side, that usually consists of doing like total cost of ownership, cost models, that sort of thing of new business proposals. It's also used within the same division in Singapore and Puerto Rico and those operations there. I'm a little less familiar with what's going on there, but in Puerto Rico, that's we do some ink manufacturing there, and in Singapore, we do various types of manufacturing. So today, I'm going to talk about two simulation examples. The first one's a semiconductor fab model, and the second one is going to be an automated manufacturing cell in one of our production facilities. So the semiconductor fab model I built was used to evaluate WIP management control levels. But first, a little bit of background on semiconductor manufacturing, in case you're not familiar with it, and why WIP management is so critical in semiconductor. So there's two peculiarities of semiconductor manufacturing that create pretty complex path through the factory, or the fab, as it's typically called. One is that the tooling costs are very high. Usually, this is actually, probably a smaller range than the more modern tools, but between $1 and $10 million per tool. So you can't just go out and buy as many tools as you want just to linearize the process. So this obviously puts a lot of pressure on capital budgets, and what you want. So it also. So you want to minimize the number of tools you have, and then, along with that, maximize the utilization as much as possible. So what this typically drives a fab to do is to organize all of the tooling into work centers, and that's similar types of processing. So photo steppers kind of get grouped together, etch machines get grouped together, that sort of thing. The second thing is the basic semiconductor process cycle. And this is right down here. Okay, so it's called depth photo etch. Basically what this is you have a wafer and you deposit a film, like a dielectric or a metal layer, and then you expose the pattern on it in a photo stepper, and then you etch back that exposed area, and then you repeat. You deposit the next film, and then all along the process flow, you keep repeating this basic cycle all the way through. And as a consequence, the wafers visit the same tools many, many, many times. So you've got a lot of reentrant flow going through the fab. And so what happens if you don't control WIP levels? Well, the basic thing is if you're working like in a work center like photo, you'll see a lot of wafer lots just piling up from different parts of the process flow. But you'll have very little visibility to what's required from a demand perspective or how the rest of the line is performing. And so you'll just select whichever wafer lot looks good to you. You'll select it, process it, and what can happen is that the work in process will just build up everywhere. You'll have very little actual throughput, and you can end up you end up concealing production issues until it's too late to respond effectively. And so, the bottom line, it becomes really difficult to meet production demand in a timely fashion. And so what HP Corvallis did was we instituted a pull card system to control WIP levels. So basically what we did was we take each product has a process flow, and we subdivided those into what are called functional moves, which is just 2 to 5 operations that that accomplish a certain function on the wafer. And we set the number of pull cards in each functional move to a limit. So we limit the number of wafer lots allowed in a functional move. So if you look down here at this chart, these bars are intended to represent the number of wafer lots that are in a functional move. Just an example here. And the little dashes there represent the pull card limit. So if you look at functional move 3, right there, it's at its limit. And as a consequence, functional move 2 cannot move any wafers into that functional move until a lot moves out of here and keeps going. And so this keeps some kind of a control over where all of your WIP is in the entire manufacturing line. So the witness model was built to evaluate those pull card levels. And the basic question here was what pull card quantity for each functional move is going to keep the product lead time at a reasonable level. And so to give you a sense for what the production environment looks like in our fab, we usually have around 20 or so products. Each product has between 50 and 180 process steps, and those are then broken down into 10 to 50 functional moves. And there are about 80 tool groups, each with between 1 and 9 tools. So this creates a lot of, I guess, complex routes through all the tool groups through the fab. So what I needed to do was develop a method to be flexible about how parts are routed through the model. And additionally, these products are always changing. They're always changing their process flows because we're doing new product development, and new products are constantly coming in and replacing them. So I needed to also make this configurable. So first, the flexible part. This is where part attributes come in very, very handy. I assign each wafer lot, which are the parts that flow through this model, 2 key attributes, a product ID and a current step, so where it is in the process flow. And these 2 are used. So down here is an example of one of the machine detail dialogues, and here's the cycle time. It uses this product ID and this current step to look up the cycle time for that product at that machine for that step. And then additionally, for the routing rule, I actually push to a function that returns a name here. And this is also using this product ID and current step and doing some calculations on how do I have pull cards available in the next one to actually push it to the next functional move. So that's the flexibility of the routing. Configurability, the way I handled that was I store all of this data in Excel. So all these process flows here. So you see, here's one process flow for product. Here's all the steps, the functional moves that step is in, the tool sets, cycle times, etc. So I load all of these, I read all of these in at the initialize and into some arrays that are then used by the parts as they're running through the model to route. So over on the right, you can see just a field of tool sets. This is not the actual layout. This is just kind of a logical model here. So the parts, would start wherever and then just bounce around based on where they need to go. So here's a little bit of a closer look at some of the tools. Each tool group has a standard structure here. So it's got an input buffer. This is the machine, which represents the tool group, and then a number of tools in each tool group. And then an output buffer in case it's going to the next functional move and it needs to store a lot there or something temporarily. So while the simulation is running, you can see some of the cycle time statistics here and also the product lead time. And typically this is actually run in a batch mode, so we don't typically just watch the simulation run. We just write the simulation output back to Excel for further analysis and take a look at the output. So a quick word about validation here. We just looked at, since our key concern here was lead times for the products, I just compared some actuals given the same the parameters, so the same demand mix, same pull card levels, and compared those. And we continue to use this on a periodic basis to take a look at, okay, what's the new demand mix, what are the new process flows, and the pull card levels, and we make adjustments as necessary. So the next example I'm going to talk about is this automated manufacturing cell. I'll go into a little more detail on this one than I did on the semiconductor fab. So this manufacturing cell is part of a line in our printing division facility, and basically we make some printer components here. And the idea behind the model here was to build a tool that can be used to identify throughput improvement opportunities and also to evaluate other ideas for throughput improvement or even for any kind of design change proposals that might come up. So over here is a diagram of the manufacturing cell, and it consists of 8 subcells, which are these blue boxes here, connected by a monorail track. And this little guy right here is meant to represent a shuttle that carries parts to all the individual subcells through the processing. And parts are loaded and unloaded here. Additionally, some of these cells do the same thing. So, for example, cell 1A and 1B, that's the same process. So there had to be some traffic control logic built into here. That was one of the things we looked at. And basically where we settled was an algorithm that looks at trying to balance the load between the two similar subcells while taking into consideration whether that production cell is down or not. So the parts continue around until they're finished and unloaded at the same place they're loaded, and then they continue on in the manufacturing process. Now, typically, we would use some kind of a spreadsheet static model to take a look at, how many of these subcells we'll need, how many shuttles we'll need, all this sort of thing. But this type of a system gets really complex very quickly because everything's interconnected. And so this is where simulation has a natural advantage over that kind of static modeling. So what you can do is you can break down all of these you can break down this system into its individual components, which were a little easier to model, and you can directly model their interaction, and then take a look at how the system performs. And additionally, out of a static model, you'll never get dynamic metrics, and that's another thing that is key for us to look at, is how how does the cycle time perform between certain operations and that sort of thing. And I'll get into a little more of that later. This is a little bit of a closer look at one of the subcells. Most of them have 5 stations inside them. So here's the shuttle coming in on the monorail track, and it stops at each successive station to process the parts. And those parts are processed on shuttle. So I modeled this using tracks and vehicles, but I don't actually unload the parts and I don't drop them off. I do the processing, then the shuttle can move to the next station, and so forth. It just started up. So okay, that works. So this is an animation of the video capture of the simulation model. So you notice I brought in a AutoCAD layout to the backdrop, which is very handy for both communicating the simulation to the users, and also for setting dimensions here, because speed is important on these shuttles, and also spacing for where the operators are walking. Like this guy right here. He is now replacing the supply that is used in this station. So that's why it's down, and that's why he's over there. And so he had to walk along this path to get there. And so you can see the shuttles moving through each of the stations. These are each of the individual processing stations inside each subcell. And they just kind of move through the whole process. And there are a couple of manual inspection steps along the way. So there's a little bit of labor involved there. So what kind of analyses did we do with this? One of the first things we looked at was how many shuttles do we need to maximize throughput. And prior to using a simulation, this would be mostly gut feel guesswork. So we wouldn't have a good idea of exactly how many shuttles would be effective. And the main thing is shuttles cost a lot of money. So we don't want too many, but we also don't want to constrain the line because we don't have some place to load the parts. So what I did was I actually used Optimizer as my experiment framework, and I ran multiple replications across a bunch of different numbers of shuttles in the model. And so this here chart is showing a box plot of the simulation, the model run results. So throughput's kind of going on the y-axis here, and this is the individual different numbers of shuttles. And so you can see it at some point, statistically, these are no different. And so you hit your maximum throughput right in here somewhere. So a follow-on question to that was, what if we increase the shuttle speed? So there's a little bit of flexibility here on the specifications of that shuttle, is that we can run it a little faster. But it will require a project to do that. So it's going to require some engineering resources, some modification to the actual shuttles. So we wanted to see if it would be worth it. And the hypothesis here is that the system's going to be quicker to respond to downtime events in any of the different subcells, which would lessen the chance of hitting starving a constraint. So prior to doing a simulation, there might be an intuitive sense that this could be a benefit, but there's no way to quantify it, and there's no way to tell whether it was actually a benefit. But with simulation, it's really easy. You just set the shuttle speed higher and rerun the experiments. So that's what's shown here. So these blue box plot here is the same scenarios, just with a faster shuttle speed. And you can see there's quantifiable difference here for these two speeds. Additionally, if that maximum throughput at the slower speed is enough to meet demand, you could accomplish that with 9 fewer shuttles over here at the faster speed. So now we can take a look and see if it's going to be worth it to invest in that project. So a third analysis that we looked at was how many frames do we need on hand to avoid stopping the line? Frames are basically just part fixtures. So the part is actually loaded into a frame, and then the part in the frame are loaded onto that shuttle and then continue through the process. And so down here I drew a little bit of diagram to try and explain this. So here's a part in the frame going on the shuttle, continue through this manufacturing cell, and then there's a few more operations that it goes through, and then the frame is separated from the part. The part continues on, and the frame actually returns back to the front of the line, sometimes going through a wash operation to clean any contaminants off. So, frames cost money too. They're not as expensive as shuttles, but they still cost a lot of money. So we wanted to minimize that quantity without sacrificing the line throughput. So basically, what I did was I modified Witness to detect the condition that there are no frames here, and then log the number of occurrences and the severity. So pretty easy to modify the Witness model to do that. And again, used Optimizer as my experiment framework to run this. So just vary the number of frames inside the simulation, which is shown down here. So these are different numbers of frames introduced into the system. This bar chart here is showing the starvation occurrences. And this line chart is plotted against the right-hand vertical axis. That's showing the severity in percent of time, percent of available time that it's starved. So you see, all you have to do is take a look and see where it bottoms out. And right in here is any more frames in the system here aren't going to do you any good. You're just going to be spending more money on frames. Additionally, we wanted to take a look. There's a question about how we transport frames within the facility. We transport them on carts. So they're accumulated, then transported on carts back to the wash operation and back to the front of the line. So the standard quantity is right here. We were wondering if you cut it in half, does it improve anything? Again, very easy to do once you've got it set up in Witness. And what we saw was there's a little bit of a benefit if you get into a situation where something is happening downstream that is causing a lot of starvation. It would have been a good idea to circulated those frames a little bit better, which matched with our, some of our intuition, but it's good to show there's some benefit, not a great deal, but a little bit. So I'm going to shift gears a little bit and talk about some of the approach and techniques I used. First of all, I designed this simulation model for use by non-simulation users or non-simulation experts. So I kept most of the inputs are set in Excel, and all the key outputs and the charts and that sort of thing are all automatically written back to Excel. And I've trained the users how to open Witness and run the model so they can watch it run and make observations there, or they can just set it to run in batch mode and then just look at the output later. Let's see. So again, the idea here is to evaluate process improvements and design change proposals. So a couple of things that were very handy in building this. First one is named ranges. I think I have in the hundreds of inputs from Excel into Witness. So I think it was vital that I use named ranges. So, and there's a couple of benefits here. One is it allows for meaningful Excel ranges. So on the range parameter in Witness, saying that it should go to cell B3, that doesn't really tell you anything of what's in B3. So if you can name it something, it might give you a clue. And additionally, it allows you to modify Excel. So insert, delete, columns, rows, that sort of thing, which is pretty handy when you're trying to work with some users that might want to see their inputs arranged in a little different fashion. So allows you flexibility there. The approach I took was I actually named my ranges to parallel the Witness model structure. So, for example, and I don't know if you can read this very well, it looks kind of blurry. So if you took, this is the hierarchy chart over in Witness. So there's a variable here called CT, and it's in the module odd, which is in the module proco1. And in Excel, I would call that proco1.odd.ct. So that's the same name that would show up in Witness as in Excel. So that allows pretty easy cross-referencing. So a couple of snapshots from the Excel inputs. So this is the main cycle time process parameters tab. So here's the processes. Here's all the individual stations all the way down until it's unloaded from the shuttle. And so here's where the users will update the cycle times per part. They can use a distribution here. So they can I left the triangle distributions in here, but you can use anything you want, like exponential. I don't know why you use exponential for cycle time, but you could. So sampling, yield loss, and also for those manual operations, you can assign the labor to it, and also shifts. So that's the main input tab there. And so all of these cells in here have named ranges associated with them. This is kind of the configuration tab. So here's where you set the number of shuttles, the shuttle speed, the number of frames in the model. And additionally, I mentioned some looking at design change proposals. Like this, I have some flags down here. So like this mini loop is a design change proposal that's kind of on the table. And so you can turn it on or off here. And the user can also look at different throughput improvement projects, some proposals. This one called OSM optimization is one example. And so you can turn it on and off here. And one more input slide. So this is the interventions. So for example, I think I pointed out in the video was that the labor over there, the operator, was showing up to replace some of the supplies at that base. And so here the user can define the consumption rate of that supply, what is going to alert that operator to show up and change it, and how much does it get set to, what's the full level. And then additionally, time to repair and whether labor is required or not, and who's doing it. And so shifting gears to some of the outputs that are written to Excel. One thing, the first thing here is something that you'll never get out of a static model, and that's the lag time between process 1 and 3. The reason we wanted to look at this is there's a potential concern that the material that's put onto the product, to the part at process 1 will expire, basically dry out by the time it gets to process 3. And so if it does that, then you've got to scrap the part. So we charted the lag time. So this is another case where the part attributes come in very handy. So you just tag the part when it hits process 1 with a timestamp, and then you measure that at when it gets to process 3, and you just collect the data and report it out. So what you're looking at here is the distribution of lag time between process 1 and 3. And so, you know, most of the parts are good, but you can tell that there are some parts out here that are beyond the spec limit that would end up as scrap out there. So you can judge, you can take a look at this against any of your throughput improvement projects or design change proposals and see what the impact is going to be, or is likely going to be to this scrap rate. Another output just kind of shows all the machine states in the entire loop. So this is in sequence of the process. So this is where the parts are loaded, right here, all the way through until they're unloaded out here. And so it's showing the busy time, downtime, off-shift time, and then the negative space up above the bars is the idle time. And then charted across the right-hand vertical axis is the throughput for the processes. This throughput degradation is mostly due to yield loss along the way. So again, this is just automatically refreshed in Excel. And a similar chart looks at the track statistics, so a little bit of the traffic in the model. So you can see right in here you've got a lot of blocking going on around process 3. So this is process 3A and 3B. And so you know there's something going on over there in the track. So a little bit of a traffic congestion there. So those previous two charts, you know, I mentioned that they are arranged in sequence of process flow. And the way I had to do that to avoid having just the data exported in alphabetical order is I actually read in the sequence from Excel. So I define that in Excel, the sequence that I want the chart to be in. So there's a couple of code snippets here in case you find this useful. But I read that sequence in here, and then at the end of the model run, Witness uses that sequence to populate an output array in the right order. And then it's just a simple matter of using the Excel write array function to drop that back into Excel in the right order. So, validation. So far we've done two major validations, comparing actual to model on a few points here, throughput, yield, and downtime. So both at a system level and then at the component level. So each of the subcells are also compared on these 3 points. And I would say, you know, I do what I call mini validations continuously. And so this is, you know, does the model do what I expect it to? Is it behaving as I think it should be behaving? You know, and this kind of goes along with debugging as well. And you know, where I can measure actual performance, like of individual components in the model, I do comparisons along the way, because these major validations, there's a lot of effort to do these, but these need to happen along the way. And so we're continuing to use this model to evaluate ongoing throughput improvement projects. So it's in use today. So I've been told that this has a very different meaning in this country. So it's basically conclusions. So, but there's no food involved today. So a couple of different points, just wanted to reiterate. So simulation versus static model. You know, simulation allows us to break a complex system into its pieces and directly model the interactions. And this avoids what happens in static models, is where you embed all that complexity into some generalizing assumptions or maybe even fudge factors. And additionally, it's straightforward to get dynamic metrics out of a simulation. So it's just not possible out of a static model. The second thing is using optimizers and experiment framework. I've found this very handy, I haven't used any. I usually use the all combinations option. I haven't used any of the heuristics, just because my simulation scenarios have not spanned the thousands and thousands. It's more in the hundreds of different simulations I need to run. So I haven't, my hand hasn't been forced there yet. But it's very handy if you can define some functions to return the metrics that you're interested in. For example, the starvation metric that I mentioned before, I just have a function that returns number of occurrences and severity. So two different functions. And you can set that up in Optimizer. Then define all the factors that you want to run your experiment, and then just let Optimizer run. Sometimes overnight if you have to. And the third thing, very handy, using named ranges. So, I mentioned this before, but it allows you to change Excel without modifying your witness model or causing errors. And for me, it facilitates easier writing and debugging of the input-output code. So.